Standard reduction potentials. Consider this cell that's composed of zinc in contact with zinc sulfate, and on the right-hand side we have a hydrogen electrode where the hydrogen is hydrogen gas with a platinum electrode. The cell diagram is zinc 2+ in contact with H+ and H2, being hydrogen at 1 atmosphere with a platinum electrode. The oxidation at the anode is zinc goes to zinc 2+ plus 2 electrons. The cathode, the reduction, the H+ picks up 2 electrons to form hydrogen. The overall reaction is zinc plus 2H+ yields zinc 2+ plus H2. We define the standard reduction potential as the voltage associated with the reduction reaction at the electrode when all solutes are 1 molar and all gases are 1 atmosphere. We're going to measure these against the standard hydrogen electrode. The reduction reaction is 2 electrons plus 2H+ yields H2. This is arbitrarily assigned the value of 0 volts. If we then attach a zinc electrode to a hydrogen electrode and measure the standard EMF, it's defined as E0 of the cell equals E0 of the cathode minus E0 of the anode. Again, here is the cell diagram. E0 of the cell equals E0 H plus H2, that's the hydrogen electrode, minus E0 zinc 2 plus zinc. The measured voltage is 0.76 volts. We assign 0 to hydrogen, so that means that the E0 for zinc 2 plus zinc is a negative 0.76 volts. This is a standard reduction potential. This time we'll hook up copper in contact with copper sulfate to a hydrogen electrode. Here E0 of the cell is 0.34 volts. Again, the cell diagram. The oxidation at the anode is hydrogen becomes 2H+ plus 2 electrons. The reduction at the cathode is 2 electrons plus copper 2+ yields copper. This is the overall reaction. H2 plus Cu2+ yields Cu plus 2H+. Again, E0 equals E0 cathode minus E0 anode. E0 cell is going to be E0 the copper 2+ copper electrode minus the hydrogen electrode E0, which is 0. So the total voltage of 0.34 is then assigned to E0 for copper 2+ copper. This leads to a table of standard reduction potentials that's in your text. They are in order of cell voltage, not alphabetical by any means. E0 is for the reaction is written. They are all reductions. The more positive E0, the greater the tendency for the substance to be reduced. The half cell reactions are reversible. If you reverse a reduction, remember you get an oxidation. The sign of E0 changes when the reaction is reversed. It becomes from positive to negative or negative to positive. And very important, changing the stoichiometric coefficients of the half cell reaction does not change the value of the E0. Let's look at the cell EMFs. Here we have 2 lithium plus zinc 2+ yielding 2 Li plus zinc. At the anode we have the oxidation. Lithium goes to lithium plus an electron. E0 is a negative 3.05. At the cathode, zinc 2+ plus 2 electrons yields zinc. E0 is a negative 0.76. Remember, E0 of the cell equals E0 of the cathode minus E0 of the anode. If we substitute in negative 0.76 and a negative times a negative 3.05, we get a positive 2.29. You can also solve this problem by saying E0 of the cell is E0 for the oxidation plus E0 of the reduction. The oxidation, remember, was the anode, the lithium going to lithium plus. The standard reduction potential for lithium is negative 3.05. That's the reduction. If you want the oxidation, it has to be a positive 3.05. If you subtract the standard reduction potential for the zinc, a negative 0.76, you get the same answer, a positive 2.29. If E0 of the cell is positive, it's a spontaneous reaction. What is the standard EMF of an electrochemical cell made of a cadmium electrode in a 1 molar cadmium nitrate solution and a chromium electrode in a 1 molar chromium nitrate solution? Cadmium gets reduced to cadmium. E0 is negative 0.40. We find that in the table. Chromium ion is reduced to chromium. E0 is a negative 0.74. Cadmium is the stronger oxidizer. Cadmium will oxidize chromium. So we're going to make the anode chromium go to chromium 3 plus, and the cathode CD 2 plus 2 electrons yields cadmium. We have 3 electrons in the oxidation, 2 in the reduction. We have to balance that out and get the overall reaction. 2 chromium plus 3 cadmium 2 plus yields 3 cadmium plus 2 chromium 3 plus. E0 of cell equals E oxidation minus E reduction. Substituting in negative 0.40 and a negative 0.74, we get an E0 of the cell of 0.34. Spontaneity of redox reactions. In terms of the free energy, delta G equals minus NFE of the cell. Under standard conditions, delta G0 equals minus NFE0 of the cell, where N is the number of moles of electron in the reaction, F is the Faraday constant, 96,500 joules per volt mole, or 96,500 coulombs per mole. Delta G0, remember, is also equal to minus RT ln K, so we can make that equal to minus NFE0 of the cell. Solving for E0 of the cell, we have RT over NF equals log K. If we substitute in the temperature 298, the constant 8.314, and 96,500 for the Faraday, we can come up with another equation. E0 of the cell equals 0.0257 volts divided by N, the number of moles of electrons in the reaction, times the log of K. Here's the relationship between delta G0, K, and E0 of the cell. What is the equilibrium constant for the following reaction at 25 degrees? Iron 2 plus 2 moles of silver in equilibrium with iron and 2 moles of silver ion. Remember, E0 of the cell is 0.0257 volts divided by N times the log of K. The oxidation 2Ag goes to 2Ag plus 2 electrons. The reduction 2 electrons plus Fe2 plus goes to iron. So 2 electron change. E0 equals E0 oxidation plus E0 reduction. That's a negative 0.80 and a negative 0.44. It's a negative 1.24 volts. If we solve for K, it's E to the E0 times N over 0.257. Substituting in, K becomes 1.23 times 10 to the minus 42nd power.